Hi everyone, welcome to Mechanical 3334, Mechanical Design Fall 2017 at the University of Texas at El Paso. Today we want to talk to you about our project 2 called Paso, and our team name is Radioactive. Our main point of our project consists of introduction, assumption, free body diagram, and calculations, finite element analysis, comparison, conclusion, and our sources. Our main focus is the buckle. We want to make sure that the design is well manufactured. We need to also analyze and optimize our buckle. The reason being is because we want our human subject to have a little bit of safety before a collision or during a collision happens. And it has to be a well-designed buckle that will prevent ejection from the driver. And our expectation continue to be having the lightweight possible buckle, make sure it doesn't fail, and we will continue to have our kind calculations and our finite element analysis. The reason why is because we also need to check the safety factor and check for failure to make sure that a human subject also did not have any injuries during a collision. Before we continue what we introduce, we need to create a little bit of guessing, educated guess. And one of the guesses we have is to have the force of the mass against gravity and force distribution. The pin will have a little different on efficiency of the buckle to figure out the strength when in action. And of course, the KT of the buckle using titanium material. Consisting of our assumptions, we created a free body diagram. A free body diagram consists of forces that are being applied onto the buckle, our dimensions, and the material, which was titanium, and all different kinds of characteristics. We also configured a little bit of unknowns, and of course, buckle dimensions can vary depending on how small or big you want the buckle to prevent injury to the person or the subject. And we also need to compare our cross-sectional area of our buckle and the distributed force. Distributed force tends to change depending on the direction of the impact and the stress applied as well. It tends to vary depending on the size of the buckle, and appropriate formulas are used to get concentrated force. And these formulas tend to vary depending on the shape of the buckle. After creating a free body diagram, we decided to move on and continue to our hand calculation. Hand calculation consists of getting different types of resources, and we decided to get results on a table that has the most accurate shape of our model. And before using the table, we wanted to have a basic understanding how our buckle are formed in our modern design. So we researched different type of material on websites, and below we found an average size of buckle. And from our understanding, we did an average size of 3 inches. Now, because the length, we wanted to have we already had a length as well. So the minimum, the hole, were going to be added. So initially, we started to use a table A15 that is also found on our textbook, and anterior local stress concentration factor from the circular part of a model, which gave us a concentration factor of approximately 2.38. And eventually decided to use batteries since it takes in consideration the pin, making it more accurate than the factor of KT of 3.44. So looking at the top right of our slide, the table A15, and if you can read the maximum stress and our areas and how we can figure out to find important factors of KT. Because on the design of the barcode, we have a rectangular shape. We utilize a formula that is derived from the equation above, and that is found in our table. And in these formulas, we can figure out using our radius and our bases, finding our area. And after that, we decided to put in the dimensions of the rectangle itself. We have the corner R and algebraically solving the width dimension and alternately label A on our MATLAB formula. In MATLAB, we use all these formulas in our length dimensions of our buckle and alternately label B on our MATLAB formula. So these are radius over here and our area and our B. They will be length dimension. And the next step is to input these constraints into the C function and input the C functions within the KT function. So additional functions within the simplifier of the KT function even more. With this, we calculated the concentration stress to be 3.84. Alright? Now, because we have different forces acting on both opening, we can determine the force that will be split into sections for the opening level of the force. And as we identified variable on KT previously in the formula, the concentration factor for the rectangle, and it manually entered on the concentration factor for a circle as well. So by keeping the majority of all the original dimensions, we found that original was length of a rectangular hole was 1.5 inches, and at the center point of a rectangular hole to be 1 inch, and the optimization of the design from a 0.5 inches thickness to a 0.25 inches thickness. And after that, we decided that our suggested was really high enough that one could actually cut it and make it more cost effective using our titanium material. And the way that we decided for the cutting proom also gave us a mass on the material that we used. And our mass initially was 0.467 pounds, and the weight will also be 211.8 grams. And on a MATLAB code, we can identify the safety factors as SF, and SF is found right here, SF, and the rectangle is to be SF1 of the circle, and the yield of safety factor of the rectangle, and the yield of the factor for the circle. Now, after initially finding our calculations, now we're going to move on and actually design our project into a important program. And before we do that, we decided to start drawing our CAD, and we're also going to initiate our finite element analysis. And below, we have our CAD schematic sheet, and all our dimensions are in entrance. And also on our pin, it will tend to change depending on the attachment of the buckle. In our FEA, we are also going to put in loads and constraints. On our left view, we put in some loads on our pin, and our pin load separation will be 1,665.5 pound force. Now on isometric front view, we have a top of the buckle force of 3,332.3 pound force, and pin load at the bottom of the pin is not integrated to present calculation, and our educated guide will be also 3,333.3 pound force. And our isometric right view, we also have a load of top of the buckle to be 3,333 pound force, and the load of the bottom of the pin also to be 1,655.5 pound force. Now, after we decided to place in loads and constraints, we decided to move on to have our FBA MECH sensitivity comparison. And when we run it on a simple stretch mesh run and on run measure stretch, we calculated to have a confidence of 0.1, and that's our element size. And after that, we decided to have a fraction of bounding factor of an element size of 0.2, and the grading factor to be 1.5 at the maximum turn angle to be 60 degrees of our polyhedron, and our conversion rates of our metron to be 5.7% of our mass stress using units of KSI. And on the bottom, it shows a solution step. So our stresses, if you can see, the maximum stress is 251.7 maximum KSI, alright? And then after, optimizing and calling to put in a modified measurement of our stress, now it's a little bit more accurate and different. In our common settings, we decided to have a less than 0.1, and that now is 2.01. And then our minimum element size is changed a little bit bigger, which is we'll also put 1, and our grading factor to be also 1. So that's a little bit different from our initial grading factor, and a maximum turn angle to be 30 degrees. Now, after we modify these settings on Autodesk Inventor, our conversion rate changed to 1.6%, and that shows a different type of bond matrix stress on our KSI. Now we have a maximum stress of 42.35 maximum KSI stress. That shows also a difference in our solution set. During our FBA environmental stress analysis result, we considered that our minimum stress that is outside of the surrounding surface and not pin or rectangle hole will be also 0 KSI. And a point of interest at a minimum stress is that anything that is not under a load or environment that we have a minimum stress, okay? And our location for a max stress is pin attachment of the buckle and the rectangle hole. The mattress Wilson is 41.69 KSI, and our point of interest at mattress is the pin load and the rectangle load produces significant stress changes on titanium material. And if you can see here, this is all of our maximum stresses, and over here of our rectangle as well. And in our titanium, we decided to also have our safety factor in the scale control MECH to be also 15, and that's unit as, and the minimum is also 2. And our weight is 0.46 pound mass. And on inventory, you can also find our general properties here, and those are important factors of our safety factor. Now, because we wanted to also preview a video of our FBA barometer stress without a pen, as you can see again, you can see our maximum stresses and our minimum stresses. Our maximum stresses again continue to be in this spot, and our max on the bottom of the pen as well. And our minimum stresses is anything on the buckle that doesn't consist of having color thematic in our FEA. Now, because we have a detailed FEA of our measure stress with the pen, you can also see a difference in here on our pen. As you can see that most of the stresses are in this spot, and it's actually very different and accurate here as well. And I wanted to explain that our maximum stress again was 41.61 maximum, and our minimum is 0. And you can also plot the difference on our stresses with pen. And that will also be an important factor when we compare into our hand calculation. And now, in comparing our FEA and our hand calculation results, we had a maximum stress on FEA to be 342 MPa, and our minimum stress to be 0 MPa. And our safety factor, to make sure that it doesn't continue to have a permanent fracture, it was 16, and our minimum was 2. And now, in the hand calculation results, we received to have 300 3.08 megapixels, and our minimum thrust to be 49.96 MCA. And our adjusting factor again are very different. We have a much higher one, and that would be 20.66, and our minimum was also 2.6. And the reason being that we had different results is because, again, our thrust concentration factor in certain different specific points of interest and the part of the tin and the shape tend to vary a lot on our design of the buckle. Now, having our basic results and our parts of the buckle, we decided that by researching certain width of the belt, of the sketch of the buckle, and the model of the buckle was also created, that we proceeded to doing the hand calculations and the FEA analysis of the buckle. So after the hand calculations and the FEA analysis, the dimension had to be changed due to several factors within the buckle. And throughout the design, the implementation process, one of the limitations we had to change was thickness in order for the safety factor to increase a little bit more on our hand and FDA analysis. And we had important challenges in this project, and that were designing was to mention we had to change for a buckle so in order that's in factor during a collision impact and make sure that our subject is safe and, increase safety factor. And finding the stress concentration for the bottom part of the buckle since there was no model of the shape was also a challenge. And also not fully knowing how to use the SEA software and having two resources and teachers ourselves how to do it in Autodesk Inventor. Now, if everyone was a little bit curious of FBA shape optimization at Autodesk Inventor 2018, well, in Autodesk Inventor, it is common to find the optimization features under the Interface Inventor and under the Mesh Design setting. The Mesh Design have to configure the important polar head-on readings of parts, and the Inventor also shows the mesh optimization of a part, shape, faces, and all the other important points of the part that anyone wants to pilot. And graphs are also available in case you want to access that. And the description of this feature in Autodesk FBA software is called Mesh View. Now, our local Mesh View is a little bit different because then it actually only focuses in one area to place in mesh, while the other parts of your shape will not have a modified local mesh view. And those things are accessed in the following interface result report. And you can configure important test environments of the buckle at the local face view or the shape face and perform the mesh view to compare and improve any design factor or my design factor and other important features to review. And that's it. Thank you very much for joining our group and our team very active on Project 2, Mechanical 334 in the University of Texas at Paso. See you next time.